Welcome to the lecture on relation between rate of loading, shear force and bending moment at a section of a beam. In the last lecture, we considered an example of a simply supported beam with an inclined point load at the center and solved for the unknown resistive axial force, shear force and bending moment developed at various sections along the beam length. We plotted the same in the form of respective diagrams. Axial forces, if at all present in a beam, appear in rare cases in comparison to the transverse shear forces and bending moments, which are the prime reasons of causing failure due to stresses exceeding the permissible limits. Also, the induced axial stresses due to tension or compression in beams are quite small in comparison to the yield or ultimate tensile strength of beam material. Hence, the beam is safe in most of the axial loads. Now, we try to have a look at the loads applied over the beam length and the plots obtained in the shear force and bending moment diagrams. For the point loads, the shear force value changes at the location of the replication points, with shear forces remaining constant between two point load locations. Hence, there is a constant shear force curve denoted by a horizontal straight line between the point loads. The bending moment curve, however, is a straight inclined line denoting a linear change of the values in between the point loads. We can hence say that the shear force at a distance x from the reference is a function of x of power 0, denoting constant values or horizontal line as the locus in the diagram. The bending moment at a distance x is a function of x of power 1, denoting linear variation. We can therefore conclude that the bending moment is a function of x of power 1 more than that of the shear force. That is, mathematically, the derivative of bending moment at any cross-section leads us to the shear force at the section in general. Or the integration of the shear force leads us to the bending moment at the section in general. At this point of time, it is difficult to make out the relation between the shear force and the loading, since the loading may not be expressed explicitly in terms of the distance x from the reference for the case of point loads. You shall eventually see in further examples that the derivative of shear force at a section leads us to the rate of loading over the beam. To clarify this further, for a uniformly distributed load applied over the beam, this is described by a function of x of power 0, meaning that the ordinate value remains uniform or same over a length, denoted by a horizontal line. For this loading, it shall be proved later that the shear force diagram shall be defined by a function of x of power 1, meaning that the shear force changes its value linearly over the length over which the uniformly distributed load acts, and it shall be seen that the bending moment diagram shall be defined by a function of x of power 2, meaning that the bending moment changes its values parabolically over the length over which the uniformly distributed load acts. Likewise, let's now assume a higher order load acting on the beam, that is, uniformly varying load over some length, which is defined by a function of x of power 1 represented by an inclined straight line. For this part of the length over which the uniformly varying load acts, the shear force shall be seen to be a function of x of power 2, that is a parabolic variation, while the bending moment shall be a function of x of power 3, that is a cubic curve. Let's try to derive the relationship more formally, that is, in an analytical way. Let's take an example of a small length del x of a beam drawn as a free body diagram in space over which an uniformly distributed load of value W kilonewton per meter acts. Let's name the two sections creating the part as A and B and the midpoint of this part as C. To maintain the small part AB in equilibrium, we need to show the shear force represented as, say, F acting upwards at the left section. The value changes to F plus del F at the section B but acting on the part to the right which we are discarding. We need the same force at section B but acting on the part under consideration. Hence we show F plus del F as acting downwards at section B acting on the part AB. We also show the resistive bending moment of value M acting clockwise at section A on the part AB, while a value of M plus del M is shown acting counterclockwise at section B on the part AB. Now, considering the part AB in static equilibrium, let's balance the forces vertically. We have the total downward forces equal to the total upward forces, that is, the uniformly distributed load represented as an equivalent point load of W times del X acting at the midspan of the part AB plus F plus del F equal the upward force F. Cancelling out F and rearranging, we have W equals minus del F over del X. That is, the rate of loading is the rate of change of shear force over the length. Now, let's balance the moments acting on the part AB. The resultant equivalent point load W times del X acting at C does not produce any moment about the same point, hence neglected. Both F and F plus del F create clockwise moments at point C. Hence, F times del X over 2 plus F plus del F times del X over 2 plus M equals M plus del M. We expand the equation and cancel out del F times del X since the product of two small quantities is a still smaller quantity very close to 0. We thus have F equals del M over del X. That is, the shear force is the rate of change of bending moment over the length. Coming next, we shall analyze various loads acting on a cantilever beam one by one. We shall consider a point load P acting at the tip of the cantilever beam in the next lecture.